Hey everybody, so today I'm going to give you some examples of how to solve problems using Snell's law. All right, you've read about Snell's law. There was some examples of Snell's law that I asked you to look at on videos. I think it was from the Khan Academy video. I'm going to show you how to set it up and solve those problems. I'm going to give you an example that you can watch as many times as you want. I'm going to be very particular, be very precise about the way I talk about things, the way I ask you to think about things in these kinds of problems. But this is how you solve a Snell's law problem. So first of all, the diagram. Let's start with the diagram so we all know what the diagram looks like and what the pieces of the diagram mean. First, this solid line here represents the surface. In this particular case, it's the surface between air and water. All right, so this is like a dish or a bowl of water where air is above the water, right? Pretty simple, pretty common everyday thing, but that's what that solid line means. And for me, and I suggest for you, the solid line should always mean the surface. Now, what I have drawn in here, and it might be hard to see depending on how the glare is hitting the screen, the board there for you, but this is a dashed line. The dashed line represents the normal to the surface. And remember, normal is just a fancy math physics word for perpendicular. So this dashed line is normal to the surface. Now, the reason that line is important is in refraction, when we're talking about the bending of light, we always describe how light bends with respect to the normal. We don't talk about it like it turns left or it turns right. We always talk about it very precisely. Does it bend towards the normal or does it bend away from the normal? Towards the normal or away from the normal? Last time I was talking to you, I talked about how when light slows down, it bends towards the normal. Like when your cart, the grocery cart, has that sticky wheel, the cart pulls in that direction. Or if your tire, one of your tires is low, the car pulls in that direction. Light bends toward the normal if it slows down. Light bends away from the normal if it speeds up. So that's the way we talk about the direction the light bends, either towards the normal or away from the normal. In this particular case, we have a red line here representing the ray of light. So this light is coming from the air towards the surface with the water. It's coming from the air towards the surface with the water. Now that's important because where the light originates matters because you have to know if the light's going to slow down or speed up. Now, how do we know that? That's where this number comes into play, the n. Remember, the n is the index of refraction. We talked about this on the last video I did for you. The index of refraction is a number that tells you relatively how fast light moves in that medium. The lower the n is, the faster light is. The higher the n is, the slower light is. So if you look at these two n's, air, the n is 1.00. Water, the n is 1.33. You can tell right away, just by looking at the n, where light will be faster. Do you know? Which medium will the light be faster in? If you said the air, you're right. Light is faster in air than water because the n is higher in water. So when the light hits the water, it's going to slow down. Now, because it slows down, it bends towards the normal. So watch, I'm going to draw this line. Okay, that's what we mean by towards the normal. In other words, this angle up here is larger than this angle down here. Okay? Now, Mr. Morgan, how did you know exactly how much? I didn't. But that's what Snell's law is going to do for us. Snell's law will tell us exactly how much it bends. So what I tried to do earlier before I started this demonstration was I tried to draw this line in so that this angle was exactly 45 degrees. Try to split the middle there. I don't have a protractor. I don't even have a ruler. I tried to do my best, but let's assume for a minute that this angle is 45 degrees. All right. The n in air is 1. The n in water is 1.33. We want to know, what is this angle? Well, that's where Snell's law is going to come into play. So what is Snell's law? I'll write it down up here. Snell's law says that n1 times the sine of theta 1 equals n2 times the sine of theta 2. So what Snell's law does is it relates these four things, this angle and that end, to this angle and that end. Now, you might be thinking, well, which one's 1 and which one's 2, Mr. Morgan? Honestly, it doesn't matter as long as you keep them together on either side of the surface. What I like to do is to say the 1s are where the light starts and the 2s are where the light goes to. So in this particular example, this would be theta 1 and this would be n1. This would be theta 2 and this would be n2. Okay? It really doesn't matter. What you can't do is mix and match, right? If you decide the 1s are above the surface, great. If you decide the 2s are above the surface, perfect. But you can't switch them around, okay? All right, so now what we're going to do is we're going to solve this equation for theta 2. Now this is where it gets tricky, and you're going to need a calculator. So if you don't have a calculator, press pause and go get your calculator and make sure it has signs. Okay? All right. So you're back. N1 sine theta 1 equals N2 sine theta 2. Let's start plugging in what we know. N1 is 1. Theta 1 is 45 degrees. N2 is 1.33. And we don't know theta 2. That's our unknown. Okay? So plug in what you know. All right. Now, I've got to solve for theta 2. So I'm going to divide both sides by 1.33. Okay? So this cancels, and I get sine theta 2 equals, I'm going to get out my calculator. Okay. Sine theta 2 equals 1 times the sine of 45. I'm going to hit equals. I didn't have to, but that's what I did. Divided by 1.33. And I get 0.53. The sine of theta 2 equals 0.53. Now, remember way back first semester when we were doing vectors and SOHCAHTOA and all that kind of stuff? Remember, when you have the sine of the angle, that's not the same as the angle. You want to know what the angle is? You have the sine equals that. You have to use that inverse sine. Now, depending on your calculator, it may be different. For this calculator, the one I have, the inverse sine, sine to the -1, is right above the sine button. Inverse sine looks like this, sine to the -1. And when you punch that button, you're asking your calculator to tell you, what is the angle that has this as its sine? What is the angle that has this as its sine? So you want to find the inverse sine of 0.53. And that's going to tell you what theta 2 is. So I'm going to do that. I'm going to find the inverse sine of the answer. And the calculator tells me, I make sure I'm in degrees, not radians, that it's 32 degrees. Theta 2 equals 32 degrees. All right. That's my answer. That's this angle. Now, it's a good idea to take a look at that answer and ask yourself, does that make sense? Is that a reasonable answer? Because sometimes you can figure out, oh, that's obviously not right, just by looking at what you got. Okay, so we got 32. Great. The math seems to say it's 32. Does that make sense that it's 32? Well, remember, we said when light slows down, it bends towards the normal. So this angle has to be smaller than that one, because that's what bending towards the normal means. Is this angle smaller than that angle? It is. 32 is smaller than 45. So that makes sense. That should be reassuring that we did the problem right. But this is how you set up and solve a Snell's law problem. All right? Now, I'm going to give you some problems to practice on. I'm going to give you some work to do that gets you to practice using Snell's law. If you get stuck, come back and watch this video again. All right? But try those problems, practice them, And on Monday, later in the day, I'll post some answers and you can see if you did them right. All right. Good luck with Snell's law, everybody.